I'm Peter from Web3 Foundation, and great to be here at the DappCon conference. Since pretty much everything that we do at the Web3 Foundation is trying to make a solid foundation for building decentralized applications, and a foundation that is also easy to use. And as part of that, we are working on a project called Polkadot, which aims to make it easier to build both domain-specific chains and general-purpose chains to support the Dapp ecosystem. And in particular, I will jump into the core element of the protocol, which is the economics of it, and tell you a few things about it, and hopefully you can get some insights from it for also designing dApps and Dapp protocols. So yeah, I'll go basically through first why do we need these economics, then jump into the core components of it, which is staking, slashing, and rewards. And then I will go through the example of Polkadot and how we design these incentives within the Polkadot protocol and different mechanisms that we have there. So generally, decentralized protocols. We need a number of actors to actually run these protocols. And they have to do things that are compliant with whatever protocol we specify. But we don't have any enforcement party, police, or anything like that to make sure that they actually perform actions correctly. So we have to rely on economic incentives to make sure that they perform good actions and they avoid bad actions. So good actions are the ones that follow the protocol and they help the protocol to progress. So for instance, that could be producing a block, or in Polkadot, it could be attesting validity of one of the constituent chains of Polkadot. And bad actions are one that can disrupt or break the protocol. So it could be equivocation in some consensus protocol or whatever other bad action within your protocol. And for all of that, that's why we have all these, usually why we have all of these scarce tokens on the blockchains is because we need these new tokens for the protocol to make sure we are able to incentivize good and disincentivize the bad actions. So how would we disincentivize the bad actions? So usually the way it's being done in proof of work and in proof of stake is we get some of the actors that are willing to maintain the network to actually invest significant resources. So in proof of work, that would be doing lots of mining, and proof of stake, it would be making a deposit or locking up stake. And then if they do something bad, so say in proof of work, they are trying to mine a parallel chain, and as long as they don't break security assumptions of the network, then they risk not getting rewarded for all the work that they have put into making that chain. In proof of stake, on the other hand, we don't have this notion of mining, and we just have the stake, and then that whoever maintains the network risks that their deposit will not be fully returned, so they will be slashed for their misbehavior. So, but why would anyone want to actually maintain a protocol if we are penalizing people and they're running the risk of not getting the money back for their efforts? So this is where rewards come in. So in proof of work, again, we have the more mining power someone puts in, the more frequently they can receive their rewards. So that means that basically the higher security they provide to the network, the higher the rewards. And in proof of stake, it's usually not more frequent, but just the rewards are some way proportional to the stake that is being submitted by the whatever actors are running the network. And now one more thing is that when we talk here about these good and bad actions, we are not talking about actions that are very trivially detected by anyone in the network. So for instance, it is pretty much impossible to introduce an invalid block in Bitcoin because or Ethereum because any single node can instantly detect it and just reject it. So these are all actions that are a little bit harder to detect or identify and thus need to be either incentivized and disincentivized. So now let me quickly recap Polkadot. So it is this multi-chain framework. It aims to allow for interoperability both between existing chains and new kinds of chains that are being built. So again, either application-specific chains that are being built for a particular dApp or general-purpose chains. It aims to provide pooled security to all the new chains that are being attached so that each new chain that one builds doesn't need to create its own set of stake or its own mining community, but the security can be provided by the Polkadot network. It aims to support heterogeneous chains. So again, these different chains, so both to support the existing ones and going into the future as we develop new kinds of chains, they should be able to attach to the network. And the ideal is, we're still figuring it out, but the governance should allow the protocol to evolve into the future and not remain stagnant, so adapt to whatever needs we have as we go forward. And the way we think about these incentives in Polkadot is, first we have certain desired properties that we would like the protocol to achieve. And we have some general understanding of what is going on based on the things that I mentioned. From there, we derive some general design principles and then figure out what the actual protocol is and what actions should be incentivized or disincentivized in what way. So I will now walk roughly through these steps to show how it works. Cool. So let's start with these with the properties and the different types of actions. So here on the left, you can see the different kinds of properties that we want to ensure, and these are also the properties that that can be enjoyed by any chain that is part of the network. And on top, you can see different kinds of actions. Some of them might not tell you much, but we'll go more in depth through some of them. So let's go through the properties. So these are important properties pretty much for any blockchain system or decentralized protocol. Some of them may be a bit more specific to multi-chain frameworks. So the first one is liveness. So we always need to make sure that new transactions are being processed, new state transitions of the different blockchains are being added so that the system doesn't stall. We need to ensure validity so that each state transition is valid, so it's correctly performed. It is very easy in a normal blockchain that is just a single blockchain where everyone checks everything, but not so easy when we have multiple chains. Availability, so everyone should be able to get the data and actually check for themselves if is everything going all right. Finality, which means that we should not be able to easily revert whatever state transitions or transactions happened. They should, once they happen, they shouldn't be reverted. Reliable messaging, which means now that we have multiple different chains running together, we need to ensure that once a message is issued from one chain, it definitely gets to the other chain. So we want to make it as easy as possible to anyone that builds an application to not have to worry if the message gets lost. So a bit like interacting between two smart contracts where you are sure that they will communicate well together. Utility, so we need to make sure that these constituent chains provide some sort of level of utility to the users. That's measured by economic means here. And we need to make sure that we don't use up too many resources when one runs this protocol. So there are some considerations there. And of course, some of these properties are partially ensured by this kind of trivially enforceable rules of the protocol that every node can check. But many have to be, many properties have to be ensured by some of these incentivized actions. And as you can see, like some of the core elements are these payable actions and slashable actions that I will talk about, which influence quite a few parameters of the protocol. And so now let's kind of list a few kind of general dynamics that fall out mostly from the things that I was saying before. So the higher we can make the penalties, the higher the security, because basically these bad actions are able to disrupt the protocol, so we want to disincentivize them as much as possible. But also, high penalties discourage parties from even participating, so we might get lower stake in the network in the first place. So we need to ensure that there are some rewards. But also, as we increase the rewards, the issue is that introduces inflation, which is a cost for an average user, because an average user that doesn't maintain the network doesn't get these rewards. The share of the network that they own or the share of the tokens will decrease. And there is also one other point where there are certain actions where penalty and reward is linked together. So for instance, for bad actions, so good actions are very easy to detect because everyone that performs the good action wants to tell everyone about it so that they get rewarded. But with bad actions, it's a little bit harder. So we need an intermediate step of reporting for bad actions. So in these cases where we reward someone, let's say for reporting, and then we penalize someone, we need to make sure that there is no perverse incentives that actually in the end reward someone from misbehaving and then reporting themselves, right? So from that, there are some principles that we can follow. So generally slashing or this risk imposed on the people that run the protocol should be as small as possible unless it actually threatens the network, and then it can be high. The inflation should be somewhat stable, or at least it should be kept as low as possible, given there is enough stake in the network. What we can use here in order to make sure that we actually get parties that are willing to get penalized a lot while not getting rewarded a lot, we can use markets for that. And we have to just make sure that anytime we reward someone, it is less than a penalty associated with the same action. So that's probably just a subset of these, but these are some of the important principles. So now let's get to the kind of the core of this proof of stake system and how does it work. So it's the nominated proof of stake with payable and slashable actions. So here the goal, we want to, as we said before already, we want to maximize the security by capturing as much as stake possible. In particular, we want any actor that is maintaining the protocol to be as highly staked as possible. So then what that means is that the minimally staked validator should have as high stake as possible, so that any action they perform in the protocol has as high of a guarantee of not being bad as possible. So this is especially important for Polkadot because there are certain actions that are just performed by a single validator that is randomly chosen. And we are also trying to minimize the rewards as long as the staking ratio is high. So if there is lots of stake, we don't have to worry about rewarding people too much. If there is very little stake, we have to reward them more so that they actually decide to stake. And the rewards should be relative to the effort that is required to perform the good actions, because we want all good actions to be performed roughly at the same rate. So if one good action takes more work than another, then maybe no one will be doing that good action. So it has to be somehow related to the work that is required. And we assume that there are certain actors out there that are willing to participate in this system. So we have validator candidates which are willing to run actual physical nodes that will maintain the network for a certain fee. And we have nominators that are willing to select some set of validator candidates for either because the validator candidates have certain self-stake, so they already risking something themselves, or they have a certain reputation, but generally they are not willing to, these nominators are not willing to run any node, but they might have capital that can still contribute to the total stake that we have in the system. So this is, I will clarify why this is not called delegators in a second. So now let's get to the actual kind of steps of the rough steps of the algorithms that we follow here in order to determine these these amounts that are being rewarded and penalized, and how do we actually capture the stake in the first place. So we'll go through these 6 steps now. So first, we gather interest. So we had this assumption that we have validator candidates and nominators. So we want them to kind of apply and say, hey, I would like to participate. So here you can see we have nominators, validators on the right. Validators, which is not indicated, can also indicate some fee that they would like to have for running the node. And the first nominator is, for instance, nominating only a first validator A, while the second nominator is nominating validator candidates A, B, and C, right? So you are able to indicate multiple parties. So now we need to actually get this stake into the system. So select a set of parties that will be maintaining the protocol, so become the actual validator. So in our case, the validator set, or a set of parties that will be maintaining the protocol, is 4, and we have 5 validator candidates. So we need to select 4 out of 5 that maximize our security. So you can see on the left is one solution to this problem where we assign now uniquely the stake from nominators to validators. But then you can see that the lowest stake validator, D or E, only has 6 tokens. So when they perform a bad action, they will not be penalized as much as on the right, where validators B, C, and D have stake 9. So this problem, in order to do it optimally, actually is an NP-hard problem, but we have a fast heuristic that is run on chain, and then we have also a few other algorithms, approximations that can be run and then submitted to the chain in order to get a better solution. And also what we can do is, besides that, we can also ensure this property of fair representation without sacrificing security, which basically means that validators should be selected proportionally to the rate at which they are nominated. So, and this is an important property to get even small nominators or small validator candidates selected from time to time. And one interesting thing here is, because you are able to select multiple validator candidates, you don't have this issue that you may have with a proof-of-stake system where you select only a single party that you nominate, because then you need to make sure that that party in the end gets elected into the validator set. While here you can say, I'm willing to trust one validator candidate that is not very popular, one that is a bit more popular, and it's actually the less popular validator candidate gets enough nominations anyways, then in the end they might get elected. So it lowers this kind of stickiness effects associated with only selecting a single set of parties, which we've already seen in existing proof-of-stake systems. Now we have the stake locked up. So this is our stake that we can work with. It comes from nominators and validators. Now, as I said, we need this system of reporting in order to actually detect bad actions. And so this is a bit, it is a bit more complex part of the protocol that I will not get into that much, but we have this mechanism of probabilistic checking in order to make sure we always detect even the bad actions as soon as possible, and escalate them through kind of a chain of checks to be detected. But then once we detect actually that a bad action occurred, then it comes time to slash. So as we said before, we don't want to be slashing a lot if the issue doesn't pose a big threat. So we basically look at how many bad actions are correlated with each other or happening simultaneously. And then if there is just an isolated case of a misbehavior, as you can see here on the left, basically you don't get slash anything or very little. So if you forgot, once to turn something on and it is not correlated with anyone else, then it's not a big deal. But then as soon as the number of bad actions approaches, or the security bounds of the protocol, which is 1/3 of malicious stake, then we basically take away everything. Yeah, so you don't get anything back, because that means it's some sort of coordinated attack potentially, or a lot of people have been overly reliant on some sort of centralized solution to run their thing. And this is exactly one important point, is that by doing this, we also discourage nominators from selecting validator candidates that run the same infrastructure or are even controlled by the same organization, and promote a bit more decentralization through penalizing correlated bad actions. But then, of course, we are penalizing these bad actions, but then we also want to reward everyone, and we want to get enough stake in the system in the first place in order to make sure it's secure. So we have this stake targeting curve that basically ensures that here on the x-axis you can see the proportion of all tokens that are being currently staked. So when there is not many tokens staked, then the interest rate that any single staker gets is very high. And as we get more stake, this interest rate goes down and down until we say at around 50% that it's actually quite a bit of stake. We don't necessarily need more. And we also, by saying that, we also cap the inflation at 10%, and then the rewards and the interest rate quickly drop off, so that we don't need to introduce excessive inflation if we have sufficient stake within the system. And so this is targeting our total amount or our staking ratio, and now how do we distribute it to all the actors that have been running the network? So as we said before, we wanted to distribute it proportional in some way to the work that they are doing. So we basically take this pool of money, this pool of rewards that we now want to issue, and then we see how much good actions, or how much has each given validator performed. And we count different things like number of issue validity statements for these different chains, number of blocks produced, uncles included, and we have this estimator that keeps track of what is a usual number of these things to be produced, and then we kind of divide it across all the validators. So if some validators haven't been as active as some others, then they will get less of the total payouts. And between also the different actions they have performed, they will get proportionally different amounts. So this is just a quick overview of the Polkadot economics. And yeah, if you are interested to find out more, please check out the wiki or the research pages. Or if you have any questions, you can maybe either ask me now or outside about how you can build on this stuff. I think also the wiki is a great place to understand a bit better what you can do right now. We'll be soon releasing a new network called Kusama, which is aimed to test a lot of these economics that I was just talking about, and some other things as well. But it should be a cool playground to see if Polkadot could be a good platform for your DApp. So thanks a lot.